Okay, so picking up where we left off, remember what we had before was the famous forms method for determining deductive validity of an argument. And the idea was that you convert a given argument into its form, figure out what the form of the argument is, and then compare that to known deductively valid argument forms. And so if the argument form that you are given matches one of those deductively valid argument forms, then you know that your given argument is deductively valid. So this is sort of the most straightforward way of determining whether you have been given a deductively valid argument or not. But there's a little bit of a trick here because you have to be careful that the argument form that you've got isn't in a sneaky way mismatching one of the famous argument forms. And so when that happens, what we've got is what they call a formal fallacy. So a fallacy, as we say here, is just any error in reasoning. We'll look at a variety of different kinds of fallacies here throughout the course, but just in general, a fallacy is any error in reasoning. And to be formal here is not sort of the opposite of casual. It's instead referring to the form of the argument, right? The structure or the pattern of the argument. So a formal fallacy is a deductively invalid argument form. And the reason it's invalid is because the form is sort of messed up. But it's messed up in such a way that it looks very similar to a deductively valid argument form. But we'll notice sort of a key thing that's wrong. And so it turns out that these argument forms are deductively invalid, although we can be fooled, perhaps, if we're not careful, into thinking that they're deductively valid. So this is why it's an error in reasoning. We think we've got a deductively valid argument, but it turns out that the form was wrong. And so it's a formal fallacy. It's deductively invalid. Okay, so just a little bit of terminology here, first of all, for the examples of formal fallacies are going to involve these sort of if-then arguments. And so we need to establish these terms. So the if part of an if-then statement is called the antecedent. So if the overall statement here was if A then B, the if A part of it would be the antecedent, whereas the then B part of it is called the consequent. And it'll be obvious why we need to establish these terms. So, for example, the first formal fallacy is called affirming the consequent. So we need to know what the consequent is. The consequent is the then B part. In fact, even more specifically, the consequent is just B, whereas the antecedent is just A. So now we've got this argument. Let's say you're presented with this argument, and you break it down and you show what the form of the argument is. And it turns out that it's this. If A, then B, says the first premise. The second premise tells you B, that is, B is true. And you want to then conclude that A is true. And so this looks a lot like modus ponens. If you look back to the previous lecture, modus ponens looks a lot like this. However, in the real modus ponens, the second premise says that A is true. It affirms the antecedent and then concludes that the consequent must be true. And so this formal fallacy has that reversed. So instead of concluding that B must be true, instead concludes that A must be true. And so that's going to turn out to be an invalid argument form, as we'll see when we look at an example. But it's sort of a tricky one that we need to point out because it does look so much like modus ponens. And as we look at some of the examples seem very persuasive. You know, we might think that they're deductively valid, but it turns out that they're not. Okay. So here's an easy example. So suppose that we substitute in, for A and B and get this argument. If the background is red, then the background is colored. Second premise tells us, yep, the background is colored, and then we conclude that the background is red. Well, this is exactly this form, if A then B, and then the second premise affirms the consequent. Notice what the consequent is here in our argument. The background is colored. And so these premises could be true, right? If the background is red, then the background is colored. Okay, that seems true. And think of the background of this very slide that we're looking at right now. If it's red, then it's colored. Okay, yeah. The background is colored. Well, sure looks colored to me. So therefore the background is red. Obviously false. And so we've got a situation where the premises are true, but the conclusion is false. And that's pretty much the definition of an invalid argument. In order for the argument to be deductively valid, it has to be the case that it's impossible for the premises to be true and the conclusion false at the same time. Okay, so here's another example. So if it's raining outside and the sidewalk is wet, the sidewalk is wet, so therefore it's raining outside. This is maybe tempting to accept as a deductively valid argument, but as the picture here shows, we could have a situation where the premises are true, but the conclusion is still false. So if it's raining outside, then the sidewalk is wet. Okay, that seems like it's got to be true. Then the sidewalk is wet. Well, here we are. We've got a situation where the sidewalk is wet, so therefore it's raining. Well, no, it's because the sidewalk is wet for a different reason. Somebody left their sprinklers on and the sprinklers are making the sidewalk wet. So we've got a situation where the premises are both true, but the conclusion is false. So that's a deductively invalid argument. So that's just a way of showing that this affirming the consequent form is an invalid argument form. Yeah. Here's another one, just to sort of reinforce how this is an invalid argument form. If Socrates is human, then Socrates is mortal. Okay, that seems fine. Socrates is mortal. Okay, that seems like it could very well be true. So therefore Socrates is human. Very tempting, because we're sort of influenced by our knowledge of the historical figure of Socrates and the assumption that he's a person, or at least was a person, and so must be human. Well, it could turn out that the Socrates I happen to be talking about right here with this argument is a dog or a cat that somebody named Socrates. So the premises in that case would still turn out to be true. If Socrates is human, then Socrates is mortal. Okay, that's like saying if my cat is human, then my cat is mortal. Okay, so then Socrates is mortal. Yep, true. So therefore Socrates is human? No, because Socrates in this case is maybe the name of my cat, which I don't have a cat, but if I did have a cat, I would probably name him Socrates. Okay, here's another one. This is sort of a sciencey example, and it's one that sort of we're very tempted to assume that this is a perfectly reliable argument, that it's deductively valid and maybe even deductively sound. So if Newton's theory of gravity and the laws of motion and orbital mechanics and all of that stuff associated with Isaac Newton, if his theory is true, then there'll be an eclipse on August 21st, says the theory. Well, let's say that there was an eclipse on August 21st, which there was a few years ago. So therefore, Newton's theory is true. So what this argument looks like is we've got a theory that made a prediction. The prediction came true. So therefore, the theory must be true because the prediction based on the theory came true. Well, notice that this is also the form of affirming the consequent fallacy. And as we saw from the previous examples, it could very well turn out that the premises are true, but the conclusion false when we've got this kind of argument form. So this is actually a deductively invalid argument form, even though we might be tempted to assume that this is a great conclusion in favor, or a great argument in favor of this conclusion. And in fact, it turns out, if you learn some more about physics, Newton's theory technically is not true. It's been replaced by Einstein's theory of general relativity. So these premises are still true, right? But the conclusion, it turns out, is false. Newton's theory is not true. It's been replaced. Okay, so here's another formal fallacy. This one is called denying the antecedent. Remember, the antecedent is the statement that's in the if part of the if-then. And if we deny it, then we're saying that it's false. And so that's what's showing up in this argument. And notice that this argument, when you just take a quick glance at it, it looks a whole lot like modus tollens. Remember, where modus tollens, we were proving something to be false. And so it looks like that's what we've got here, but in the real modus tollens form, the second premise denies the consequent. So it would be if A, then B, and then second premise says not B, and therefore we conclude not A. Whereas this fallacious version, the denying the antecedent fallacy, has the second premise and the conclusion swapped. So it says the second premise tells us that A is false, and then we conclude that B must be false. And again, with some examples, this could be sort of, we might think that this is a deductively valid argument, but we have to be very careful that this argument form is always going to turn out to be deductively invalid. So again, let's use the background color example here. So if the background is red, then the background is colored. Okay, the background is not red. Okay, that also seems true. So therefore the background is not colored. It's like, problem, right? Clearly the background of this slide is colored. It just is blue, not red. And so we have a situation where the premises are true, but the conclusion is false. And so we clearly have a deductively invalid argument here. Here's another example. If Bill Gates is an oil tycoon, then he's wealthy. Like, okay, that's one way to get wealthy, is to be an oil tycoon. Then the second premise tells us, oh wait, Bill Gates is not an oil tycoon. So we might be tempted to conclude that Bill Gates is not wealthy. Like, well, if you know anything about the history of computers and retail and operating systems and all of that, you know Bill Gates is very wealthy, one of the most wealthy people. It's just that he didn't get his money from oil. So we've got a situation again where the premises are true, but the conclusion is false. So we've got a deductively invalid argument. So that's just a way of showing that this argument form is always going to end up being deductively invalid. And it's such a common one that, again, they give it this name, denying the antecedent. So a little bit more, some of this, maybe it's become obvious, this technique that we're using here for figuring out whether these very basic arguments are deductively valid or deductively invalid. And so the way that we do it is we identify the specific antecedent and consequent involved in our argument and just label those appropriately. So if A, then B for something like this, for a statement like this, if Socrates is mortal, then if Socrates is human, then Socrates is mortal. We identify the antecedent statement and label it A, identify the consequent statement and label it B. And so here's some other ways. The standard form when we're doing this is the affirmative. So Socrates is human. That would be the standard form. And so we would just give that a single capital letter, like capital letter A. But if the statement was actually telling us Socrates is not human, then we take the standard form, the affirmative, Socrates is human, and put a not in front of it, right? Just say not that. So Socrates is not human. That can't just get its own single letter all by itself because it's a negative. Only a positive one, like the first example, Socrates is human, that gets a single letter. But if it's a not statement, then we have to indicate that in our symbol here. So Socrates is not human would have to be symbolized as not A. Or, Socrates is mortal, we could just give that a capital B. But if we're saying that Socrates is not mortal, then we can't just say C or something. We can't just give it a single letter. We have to indicate that it's a negative, that it's not B. Okay. Yeah, the conclusion, Socrates was mortal. Socrates is not mortal. If that's the conclusion, then not B. If Socrates is not human, then that symbolizes just not A. And then once we've done all of this symbolizing, right, we convert sort of the regular English sentences into these symbols and put them in the right order, then we can compare them to one of the argument forms that's on the list and see if it's a deductively valid argument form or a deductively invalid argument form. So if we look at the whole argument altogether, we can see how it gets converted, right? If Socrates is human, then Socrates is mortal, becomes just if A, then B. And then the second premise telling us Socrates is not mortal. Remember, B is the consequent here. And so if we say Socrates is not mortal, then that's not B. And the conclusion, Socrates is not human, that's not A. By the way, that is the modus tollens argument form, so that would be deductively valid. Let's look at some other examples real quick here. So here's one you might be given if there's some astronomical object. We'll just call it X. And if X is a planet, then X orbits a star. X is a planet, so therefore X orbits a star. Okay, is that deductively valid? If you're real familiar with the argument forms, you might be able to just recognize this, but it can be useful to go through this process of substituting the antecedent and consequent statements with just capital letters. So it would look like this, right? That X is a planet, just label that A. X orbits a star, label that B. So let's look at this. Then looks like this, right? If A, then B. The second premise is that B is true, so therefore we conclude that A is true. Well, if you go up higher, we could go up to affirming the consequent. There it is. And we see that that's the argument form that we've got here that we ended up with when we substituted in symbols for those statements. So let's go back down to where we were. Yeah, so we see that it matches the affirming the consequent form, and we know that that's a deductively invalid argument form. So we now know that this is a deductively invalid argument. And if we want to sort of like reason it out using the content of being a planet and being a star and that sort of orbiting a star, well, what if X is a comet? So if X is Halley's comet, then if Halley's comet is a planet, then Halley's comet orbits a star. Okay, yeah, that would be true. If Halley's comet is a planet, then Halley's comet orbits a star. That's fine. So Halley's comet orbits a star. Yep. So Halley's comet is a planet? No, it's a comet. So we can see how that works out to be invalid. Okay. Just a couple other quick examples here. Same basic thing, but just a different argument form that we're going to end up with. So X is a planet, that's still just labeled as A. X orbits a star, still just labeled as B. Now we've got a negative in the second premise. It's a negative version of the consequent statement. So we put in not B. And then the conclusion is a negative version of the antecedent statement. So we say not A. And that gives us this argument form. And we see, if we compare it to the known argument forms that we've already looked at, we can see that this is the modus tollens argument form. We know that it's a deductively valid argument form. So we know that this argument is deductively valid. Okay. It gets a little trickier when we're dealing with what are called categorical statements. And I didn't use this term before, but the very first argument that we looked at in the previous lecture about Socrates being mortal, that was actually using categorical statements. So all humans are mortal, that's a categorical statement. And so if we're using this method that we were just looking at, and scroll back up to it here, where we substitute in capital letters like A or B for whole statements, then that's going to give us a problem when we're dealing with categorical statements. Because if we have something like this, all X's are Y's, like all humans are mortal things, right? All humans are mortal, or all apes are mammals. If we substitute in a capital letter for that whole statement, it'll just be a single capital letter. And so if we get to argument like this, all humans are mortal, well, if we just used a single capital letter to represent that statement, it would just look like this, right? We just use capital letter A to symbolize that whole statement. Then Socrates is human, that's a single statement, so we would just use a single letter. Let's just use letter B. And then, so therefore Socrates is mortal. Socrates is mortal is a single statement, so we'd have to come up with another letter to symbolize that whole statement. And now the argument form is this: A, B, therefore C. Like, that's just so vague and generic that we have no way of seeing whether this is deductively valid or not. Just as it stands, it's clearly an invalid argument form. Just any false statement for letter C, and then true statements for A and B, and you got a deductive, or you have a situation where the premises are true and the conclusion is false, so it's a deductively invalid argument form as it stands, but it's not very useful, right? And so when we're dealing with these kinds of categorical statements that say like all of one thing is another thing, like that, all humans are mortal, or all apes are mammals, or some of these other categorical statements like some X's are Y's, some apes are gorillas, or no X's are Y's. That's also an example of a categorical statement, like no apes are fish. That's a categorical statement about apes. So in that kind of a situation, we have to change our strategy a little bit. One of the ways that we can do it that I won't talk about further here is drawing Venn diagrams to represent the categorical statements. And that will help to give us some insight as to whether the arguments we're dealing with are deductively valid or invalid. So if we had a situation where all A's are B's, then the circle for A's is completely inside the circle for B. So there's everything that belongs in the A circle also belongs in the B circle. So that's how we would represent all A's or B's. But if it turns out that the categorical statement we're dealing with is no A's are B's, then we would have two completely separate circles, right? If all the A's fit into this circle, notice that none of them fit into the B circle. So that matches the statement that no A's are B's. Some A's are B's. Well, then we've got some overlap here. The A circle, some of it is included in the B circle. So some of the A's are also B's. And then over here, some A's are not B. Again, we've got some overlap here where maybe some of the A's are outside the B circle. And so, like I said, we'll hold off, like in chapter 6, we'll see how we can use Venn diagramming this way to show us whether a whole argument involving categorical statements turns out to be deductively valid or invalid. But we'll hold off on that for chapter 6. That'll be a nice little surprise for us when we get there. But for now, let's look at this other method for determining deductive validity or invalidity of arguments involving these categorical statements. So first of all, you need to convert the argument to a generic form, if it's not already like that, involving just A's and B's, as opposed to like the whole regular English sentences. And notice also the other thing that we've got to do here is instead of using capital letters to represent the whole statement, we're now back to what we started off with at the beginning of chapter 1, which is using capital letters to represent individual terms or predicates instead of whole statements. So we convert this to a generic form, as I'll have a couple of examples coming up here. Then we try to find some substitution for A and B and whatnot that we've got in the argument to make it turn out that the conclusion is false, but the premises are true. And if we've got a situation where the premises are all true and the conclusion is false at the same time, then we know that we've got a deductively invalid argument. So let's look at this. So let's say that you're given some argument in regular English paragraph or something, and then you convert it, you realize that here's the form. What this argument is actually saying is that all A's are B, all B's are C, and so therefore all A's are C. And you want to see if that's a deductively valid argument form or not. Well, you start with a substitution for A and C that makes the conclusion false. So we're going to kind of work backwards here. So you come up with something, regardless of what you started with, whatever sort of the English sentences were that you started with. Now you've just got this form here in front of us. And now you just want to come up with some terms for A and C to fit in there that are going to make that conclusion false. Then you take that A and C and substitute them in appropriately in premises 1 and 2. Then you try to find a substitution for B that makes both of those premises turn out to be true. And if both of those premises are true, while you intentionally set the conclusion to be false, then you know you've got an invalid argument. But if you just cannot come up with any possible substitution for B that ends up making the premises false while the conclusion is true, then you know you've got a valid argument. So let's look at an example. So same form that we started off with. Let's say we've got this form. Well, let's do that first thing. Start with a substitution for A and C that makes the conclusion false. So I just came up with something, right? So all lions are crocodiles, right? Clearly that's false. Then I'm going to use that substitution for A and for B and put those into where I find, I'm sorry, for A and for C, and put those into the premises where appropriate. So that gives us this. All lions are B, and all Bs are crocodiles. Therefore, all lions are crocodiles. Now, is there anything we could substitute in for B that would make those premises come out true? Well, let's see. All lions are fierce. So all fierce things are crocodiles? No, that's not going to work. All lions have hearts. So all things with hearts have crocodiles? No, that's not going to work out. So yeah, it doesn't seem like there's anything we can come up with for B that could make both of premise 1 and premise 2 both come out true. And so that tells us that what we started out with here was an argument form that is deductively valid. We just can't come up with any way of making this deductively invalid. We can't come up with any way of setting this up so that both premises are true and the conclusion is false at the same time. So how about this one? So here we've got an actual like English argument that somebody's given us, and we're wondering whether this is deductively valid or not. So the first thing, again, like always, we convert it into sort of a standard form involving just A's and B's, as opposed to sort of all this perhaps somewhat confusing English wording here. You know, you might look at this and say, this seems like a plausible argument, but is it deductively valid? Well, yeah, convert it into this sort of generic form here. And then once you've got that, start substituting in some things that just to force the conclusion to turn out to be false. So let's see here. What could we substitute in for A and C to make the conclusion false? Well, I could say all whales are not mammals. So for A, I'd put in whales, and for C, I'd put in mammals. Well, this is clearly a false conclusion. We know that all whales are mammals. So it's false to say that some whales are mammals. So we're off on the right track here. Now we take whales for A and mammals for C and substitute those in the first two premises where appropriate. And we get this. So all whales are B, some B are not mammals, so some whales are not mammals. Okay, now the trick. Can we come up with some substitution for B here, something that we can put in for B that's going to make both premises turn out to be true? Well, in this case, there is something. Animals. What if B was animals? Then all whales are animals? Yep, that seems true. Some animals are not mammals? Yep, that seems true. So some whales are not mammals? Well, that's false. And so what we've got here is a situation where both premises are true, but the conclusion is false at the same time. So that tells us this is definitely a deductively invalid argument. Okay, so that's just sort of a somewhat complicated way of spelling out what they call the counterexample method of determining whether an argument is deductively valid or invalid, and specifically an argument involving these kinds of categorical statements. We come up with counterexamples, right? We come up with examples to substitute in for A, B, and C such that the premises turn out true and the conclusion turns out false all at the same time. And that tells us that the argument is deductively invalid. And if we just cannot come up with a consistent substitution for A, B, and C that gives us a situation where the premises are both true and the conclusion false at the same time, if we just can't come up with any substitution that makes that the case, then we know that we've got a deductively valid argument involving categorical statements. Okay, so that's it for this little lecture. So the second part of the first chapter, and I'll go ahead and stop there.